right, so let's do computer vision, which is, of course, one that gets a lot more attention. And we're going to do a famous computer vision task here. There's a thing called the MNIST Library of Clothing. They got these pictures of clothing, and they're in 10 categories: t-shirts, trousers, pullovers, dress, and so on. And your job is to categorize them into these categories, and you have labeled data. The images come in, and you know the right answer for each image. So now we're going to do this. We're going to make a neural network like this, where you feed in the input image. This is going to be 784 pixels, is how many pixels each grayscale. You separate them into independent inputs. And then you have a layer of hidden neurons processing them, and then you sort them into 10 categories. Now, by the way, I used to do computer vision models for the human brain. It's one of the research projects I did years ago. I immediately rebelled when I saw this. This is appallingly stupid. If a human looks at this image, they don't process each pixel independently. They notice right away, oh, there's this black background. All that background doesn't matter. There's an edge here. There's a stripe here. You would have a layer that picks out meaningful features like an edge or a stripe, and then you would work on those tokens. This doesn't do that. It treats each pixel as a totally independent piece of data. So if there's a black pixel here and a black pixel next to it, it doesn't remember that it was next to it. It doesn't retain any information about spatial location of the pixel here in a meaningful way, which is ridiculous. It throws away the most important bit of data right from the start. But it can learn to do this task to some extent. So let's try this one. And this is part of why AIs are so very strange. If you don't program them so they're designed like humans, they're going to solve the problem in a strange way that is not at all close to the way humans solve it. And that's why you get these weird defects where you can fool an AI by adding a few dots somewhere that would never fool a human. So here it goes. Getting ready to go. All right, there we are. So it's downloading the data, getting it ready. Okay, it's going to do 5 epochs of training. So here it goes. All right, so there's the loss, which is the error, 0.6. So now it takes a step to improve all those parameters. And the loss goes down to 0.3, and on you go. All right. All right, there's the fourth one. See, it's now taking about 10 seconds to do each epoch here, which is still not bad. Google gives you a lot of processing power for free. That's why I always send my students here. It doesn't matter what you have. You could have a tablet or a cell phone. You could still be doing all this stuff. It's all in the cloud. So there we are. And all right. Now it has done it. Now I go back to my instructions. All right, so it runs it, gets the loss down to a small number. And one thing to point out, there's 2 loss numbers here. Let's look at the accuracy. It's 89% accurate on the training data and only 87% accurate on the test data. This is what you do, by the way. You don't train on all the data. You set aside a portion to test it, like 20%. So you train it on 80% of the images, and then you test it with new images it has never seen before, drawn from the same population. And what you're worried about is underfitting and overfitting. If you underfit, it will not learn to do the job. If you overfit, this is a little bit of overfitting. It's better at categorizing the training data than the test data. Now, if you train it too long, it will memorize not only the trend, but spike each individual noise point. It doesn't know the difference between noise and signal. So it will get not the underlying trend. It will specifically learn these particular garments, and then when you show it new garments, it won't be any good at them. So this is pretty good, 89% on the training data, 87% on the test data. So we can take a look at the results for 20 test images here. Let's make a new block of code. All right. And so what you see here are there are 10 neurons at the output, and the neurons output a signal, which is the chance that it is in that category. So the right answer for this one is 9. This is column 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And so you see, it decided there was a 94% chance this was a 9 and a 5% chance that it was a 7. So it got that one right. If you want to see one it got wrong, you want to find small numbers here. Like 6, it was pretty confused about, only 59% chance it was 6. And some of these it's going to get wrong. There's 4. Yeah, this one. This one's really a 4, but it decided it only had an 18% chance of being a 4 and a 76% chance of being a 2. So that one is wrong. Now, I went for a range of 20, so that's from 0 to 19. 19, 18, it looks like number 17 I got wrong. So let's take a look at that one. Here's some images. All right. So to view the images and try to understand why it got them wrong, I want to look at the first image it got right and number 17, which it got wrong. And it varies because there's some randomness in the process here. So here's one it got right, and there's one it got wrong. Holy cow. That piece of junk. It couldn't tell you what that was. It couldn't tell if that was a 2 or a 4. If you go back here, there, 2 is a pullover and 4 is a coat. And I don't even know the difference between a pullover and a coat anyway. And I guess the AI, I couldn't tell whether that was a pullover or a coat, and I don't really blame it. I think a human would have trouble telling the difference. So it's making sense. It's doing a reasonable attempt to fit these things. All right. And I think that's all I wanted to say about that. You can do a model summary to see how many parameters there are, and there's 100,000 parameters in that model. All right, so let me stop this one.